All right, today we're going to tackle one of the most famous sequences out there in both math and programming, the Fibonacci series. And we're going to uncover how a solution that looks incredibly elegant on the surface can hide a surprisingly inefficient secret. Have you ever wondered what the spiral of a seashell, the petals on a flower, and the arms of a swirling galaxy all have in common? It might sound random, but they all echo this simple, beautiful mathematical pattern. And nope, it's not a coincidence. It's like a fundamental code that nature just seems to love. So today we're going to pull back the curtain and see what it's all about. So, what is the secret code? Well, it's the Fibonacci sequence. And in this first part, we're going to break down exactly how it works. It's simpler than you might think. Okay, the rule is actually incredibly simple. To get any number in the sequence, you just add the two numbers that came right before it. That's it. In math terms, you see it written as f of n equals f of n minus 1 plus f of n minus 2. But for any of this to get started, you need a starting point, right? And those are our base values. The sequence always kicks off with 0 and 1. And here's what that looks like in action. You start with 0 and 1. You add them together, you get 1. Now our last two numbers are 1 and 1. Add them, you get 2. Now it's 1 and 2, which gives you 3, then 2 plus 3 is 5, and it just keeps going like that, creating this infinite, elegant chain. Pretty cool, right? Now that's the math, but how do we get a computer to do this? Well, one of the most intuitive and frankly elegant ways is through a concept called recursion. The best way to think about it? Imagine a function staring at itself in a hall of mirrors. You see, recursion is basically when a function calls itself to solve a smaller piece of the exact same puzzle. It's like if you ask it, hey, what's the fifth Fibonacci number? And the function says, I don't know, but I can figure it out if you tell me the fourth and third. And this just keeps happening, going deeper and deeper, until it finally hits those base cases, 0 and 1, which it knows the answers to. And look at this. This C code is a perfect mirror of that idea. First, it checks for those base cases. It asks, is the number you gave me a 0 or a 1? If it is, boom, it stops and hands back the answer. That's its escape hatch. If not, it moves on to the recursive step, where it literally performs the formula. It calls itself for n minus 1, calls itself for n minus 2, and just adds the results. It's a beautifully direct translation. So the code looks clean. It looks simple. But what actually happens behind the scenes when we run it? Let's trace the calculation and really see this hall of mirrors in action. So to find, say, the fourth Fibonacci number, the function immediately splits. It says, I need fib of 3 and fib of 2. But to find fib of 3, it has to split again into fib of 2 and fib 1. And to find that fib of 2, it needs fib 1 and fib 0. You see this branching out? It's only when those calls finally hit rock bottom, the base cases of 0 and 1, that they can stop digging and start passing answers back up the chain. And when we run this process in a loop to get the first 5 terms, it works perfectly. We get the sequence we expect, 0, 1, 1, 2, 3. The logic is solid, the output is correct. So, what's the problem? To see it, we have to look under the hood. And this is where the story takes a sharp turn. This diagram is called a recursion tree, and it shows every single function call that happens just to calculate fib 5. Now, look closely. To get fib 5, we need fib 4 and fib 3. But wait, see fib 3? It gets calculated over here, and then again over here, from scratch. And fib 2? It's calculated once, twice, 3 separate times. We're doing the exact same work over and over and over again. This brings us right to the heart of the matter, the elegant trap. Our beautiful, clean, recursive code, the one that so perfectly matched the math, has a massive hidden flaw. What is the real cost of all that wasted effort? Yeah, the code is easy to read, but is it actually practical? Let's put a number on this inefficiency. This right here, O of 2 to the n, describes the time complexity. Now, don't let the notation scare you. All it really means is exponential growth. And in programming, that's bad news. It means for every single new number we add to the sequence, the amount of work our program has to do roughly doubles. Think about it. Calculating fib of 20 is almost instant, but calculating fib of 40 isn't twice as slow. It's more than 1,000,000 times slower. It could take minutes, maybe hours. That's exponential growth working against us. So, the reason it's so slow comes right back to that tree we just saw. The program basically has amnesia. It has no memory. Every time it needs to calculate fib3, it starts from scratch, even if it just did that a millisecond ago in another branch of the tree. This brute force method just isn't built to scale. And this, right here, is the elegant trap. On one hand, the code is beautiful, it's clean, simple, and it reads just like the mathematical formula. But on the other hand, the performance is, well, it's a total disaster. It creates this huge explosion of repetitive work that grows exponentially. The code's simplicity completely masks how incredibly inefficient it is in practice. So why does all this matter? Because this is a classic lesson in computer science. It's not enough for code to be correct. It also has to be efficient. Understanding how an algorithm actually does its job is what takes you from just writing code to being a real problem solver. Elegance is great, for sure, but efficiency is what makes a solution actually work in the real world. This entire problem, all of it, stems from recalculating the same values. So that leaves us with one last big question. What if our function had a memory? What if, instead of starting from scratch every single time, it could remember the values it's already calculated and just look them up? How much would that change the story?